Let's look at acid-base properties of salts. A salt is another name for an ionic compound. So it will have a metal and a nonmetal. It could have a metal and a polyatomic ion, and it could also be two polyatomic ions. When a salt dissolves in water, it will always break up into its ions, and you should always assume that at least one breaks apart, so even if the solubility is very, very low. Under certain conditions, these ions can behave like acids and bases, affecting the pH of the solutions. When they react with water, they can form acids, and so this means that the salt would make a hydrogen ion, or they can make bases, which means that the salt somehow makes a hydroxide ion. And some salts are neutral with a pH of 7. Please memorize this chart. Let's take a look at it though, because a lot of it you can kind of figure out. Let's start off with our neutral anions. So these are always listed after the cation, but all of these come from strong acids. So my Cl- comes from hydrochloric acid. My Br- comes from hydrobromic acid. NO3- comes from nitric acid. If we go with the observation that strong acids yield weak conjugate bases, these are my weak conjugate bases. They are so weak that they end up being neutral. So they are not able to be a base or an acid. Let's look at our neutral cations. So these are written first in the salt. If you notice, all of these come from strong bases. So my lithium ion comes from lithium hydroxide. My strontium ion comes from strontium hydroxide. So again with the pattern, if I have a strong base in my reactant side, then I'm going to have a weak conjugate acid. So these will be neutral. Next comes these basic and acidic anions, and these are going to come from the weak acid. So a weak acid would give a stronger conjugate base. And so these would be basic in solution. When you dissolve the salt into water, we would end up with a basic solution. The Cn- comes from HCN, which is a weak acid. This weak acid has a stronger conjugate base, the Cn-, and all of these have that same thing. Our acidic anions come from polyprotic acids, so acids that have more than one proton that they can donate. So this one comes from H2SO4, which is also a strong acid, and this one comes from H3PO4, which is a weak acid. Our acidic cations, these ones are metal ions that are pretty positively charged. So if we look here, we have a +2 and we have a -3 here. And then we also have ammonium ion, comes from ammonia. And ammonia is a weak base, and so the NH4 plus, the conjugate acid, is stronger. Whenever you have a neutral salt solution, that means that you need a cation from a strong base. In order to form a neutral solution, you need to have a cation from a strong base and an anion or a conjugate base of a strong acid. For example, sodium chloride, when you put it into solution, it does make a neutral solution. And the reason why is the sodium is from a strong base, and the chlorine, the chloride ion, is from a strong acid. And so with this combination, we're going to get a neutral salt. So remember, the stronger the acid or base, the weaker the conjugate acid or base. So if you're starting with a strong acid and a strong base, then you are going to have a neutral salt. Whatever the pH of the solution you add the salt to, that pH will stay the same. So if you add a neutral salt to water, which has a pH of 7, then it will stay a pH of 7. However, if you add it to an acidic solution, if it has a pH of 2, it will stay a pH of 2. Some other neutral salts would be Ki, and the reason why is the K is from potassium hydroxide and the I is from hydroiodic acid, and both of those are a strong base and a strong acid. And this next one would also be neutral. We get calcium from calcium hydroxide, which is a strong base, and this is the perchlorate ion, and it is from perchlorate acid, which is a strong acid. So you kind of have to look where that ion came from, and if it came from a strong acid or a strong base, then it would be neutral in solution. Weak acids, weak bases, and their salts. When you have a weak acid, when you put it into water, it will dissociate into its ions. And this is an organic acid, so that little H is on the end in this case. Sometimes they write it at the beginning, you just have to be aware. What will happen to this conjugate base? So if I have a weak acid, then that means that my conjugate base is quite strong and it drives the reaction backwards. So I can change my equilibrium arrows. I can have a longer backwards one and a shorter forwards one. If that conjugate base is part of a salt, you're going to see the same thing. It will be the driving force of the reaction. So let's look at the following salt. So I have sodium. Now this is from sodium hydroxide, so I know that just the sodium ion, that this is going to be neutral. So it's really not going to have an effect on any equation. It's not going to be the driving force of any reaction. What will be our driving force is this acetate ion. So when I take this acetate ion and I put it into solution, so I'm going to add it to water, it is going to take a hydrogen ion from the water. So I'm going to get CH3COOH, and then I will have the leftover, which will be hydroxide. So you can see that this is a weak acid and its conjugate base is quite strong, and when is put into solution as part of a salt, then it is going to behave as a base, and this will be at equilibrium. Let's look and see what a weak base does. So first of all, I have my ammonia and I'm going to add it to water. So with the weak bases, you often have to put the water on the left hand side, so it has a hydrogen ion that it can take. Remember, bases gain protons or hydrogen ions. So I have a weak base, so I'm going to just use a little b for the weak base, and it makes a quite strong conjugate acid. And so this conjugate acid is the driving force of the reaction, and it is going to cause the reaction to form more reactants. So I really have a longer arrow going backwards than I would forwards. Now, how will its conjugate acid behave? So if I were to take this component and have it as part of a salt, you are going to see that it be a driving force. And so I'm going to get the following reaction. So I'm going to have this ammonium ion, and it is going to lose a hydrogen, and then I will have that ammonia. And it will still be at equilibrium. Salts that produce acidic solutions. So in acid solutions, the salts are derived from a strong acid or an anion and a weak base, the cation. And here's two examples here. So I have ammonium chloride. I put that in water. It makes ammonium and chloride ion. I know that this chloride ion comes from hydrochloric acid. So I know that this chloride ion is going to be neutral. However, this NH4, this is the conjugate acid of my weak base, and so it's going to go on and do the following reaction right here. So it is going to dissociate into a hydrogen ion and then the ammonium. And again, the reason why is it has to do if you have a weak base, you're going to have a stronger conjugate acid. And then as a salt, it will drive the reaction and it will give us an acidic solution. Salts with small, highly charged metal ions will also do this. So a good example of a highly charged metal cation would be aluminum or chromium or beryllium or iron. So when put into water, it forms a complex with the water. So that's why we have 5 water molecules that are attached to this aluminum ion. And because those waters are pulled in by that positively charged cation, then one of the hydrogen ions on the water, it can dissociate because it's just loosely held. And so because of that, then this produces an acidic solution. Let's look at a picture of this. Hydrolysis of metal ions, again, the water molecules will be attracted to those cations, and you can see on the second example how you have a positive 3. It's going to be a very strong attraction, much more than this +1. And so this is the complex with water that it forms. So here's my little positive cation right here. And then these are all the water groups around it. And because of the strong attraction, the OH bond is weakened and one of these hydrogens can come off. And when it does that, then it produces an acidic solution. The higher the charge of the cation, the more acidic the solution will be. So you possibly could have more hydrogen ions come off. For the following salts, classify them as either an acid or a base or neutral. So what we have to do is we have to pick apart the ions and figure out if they come from a strong acid or a strong base. Then we would know that they would be neutral. If they come from a weak acid, then I know that I have a stronger conjugate base. If they come from a weak base, then I know I have a stronger conjugate acid, and the solution will be an acid solution. So let's do our first one. So I have strontium. I know that strontium is in a strong base. And this CN comes from HCN. So this is a weak acid. So I know that what's going to happen when I put this into water is strontium is not going to do anything, so this one's going to be neutral. But my CN ion, because it comes from a weak acid, then it's going to act like a base. So I'm going to add it to water, and I will get HCN, and then the important part here is it will be a basic solution because it forms this hydroxide ion. Our next one is barium chloride. So barium, this comes from a strong base. And this chlorine, it comes from a strong acid, HCl. Where they're both coming from a strong base and a strong acid, then I know that this is going to be a neutral solution. Potassium fluoride, my potassium comes from potassium hydroxide, and this fluorine is going to come from hydrofluoric acid. So this is a weak acid. So when I add that fluoride ion into solution, it's going to act as a stronger conjugate base. This is going to be a basic solution if I am starting from the salt. So put it at equilibrium, and then I'm going to have it take a hydrogen ion from the water, and then I'll have a leftover, my hydroxide. So this is a basic solution. Sodium nitrite is what this one is. So sodium is from NaOH. The NO2 is from HNO2, so this is nitrous acid. So I am going to, because this is a weak acid, therefore I'm going to make a basic solution. So NO2 and add it to water, and it's going to take a hydrogen ion from the water, and it's going to make hydroxide, so this is going to be a basic solution for this salt. And for this next one, so this looks like an organic cation, and this comes from the weak base, CH3NH2, and this chlorine comes from the strong acid, HCl. So this is a strong acid, and then this is my weak base. My strong acid, this chlorine's not going to affect anything. Instead, it's going to be this ion from the weak base. And it is going to dissociate and give off that hydrogen ion. So this is going to be an acidic solution because it forms this hydrogen ion. So on all of these, you need to be able to pick apart each cation and anion and figure out if it's going to act as a base or an acid. So why is finding the pH of salts useful? We are interested in the pH for all kinds of important reactions. And a good example of this is controlling the pH of our blood and also of water sources in our environment. So these things contain dissolved salts, and which will affect the pH. How do we do pH calculations for solutions containing a salt? It's going to be very similar to finding the pH of a weak acid or weak base. However, you just need to think through one extra step. So you need to think through, is it going to make an acidic or a basic solution? If it's going to make an acidic solution, you need to make sure that you use a Ka. If it's going to make a basic solution, then you need to make sure that it makes a Kb. Let's calculate the pH of a 0.3 molar sodium fluoride solution. For the hydrofluoric acid Ka, it is 7.2 times 10 to the minus 4. And here is the dissociation equation all ready for us. So we need to think about this. Is this going to form an acidic or a basic solution? So let's look at the sodium ion. So this sodium ion, it comes from sodium hydroxide, which is a strong acid. So this is going to be neutral. The fluorine, however, it comes from hydrofluoric acid, and this is a weak acid. So that means that this is a stronger conjugate base. So that means in solution, it's going to act like a base. So there is my equation that I'm going to be using. Now, because it's a base, they gave me a Ka, but I need a Kb. To find the Kb, I'm going to divide the Kw by the Ka. And I get 1.4 times 10 to the minus 11. So let's go ahead and make an ice chart and put in what we know. So I know that I start off with an initial concentration of my fluoride ion as 0.3. And then my water is a liquid, so I'm not going to even fill it out in the ice chart. And initially, I don't have any dissociation. And then the change is I'm going to lose a little and then gain a little and bring everything down. I have 0.3 minus x, and I have x, and I have x. And I'm going to assume that this x is tiny. So I'm just going to get rid of it because it's going to make my calculation easier. So in this problem, our objective is to find out what the OH is. Once I find out what the OH is, then I can find out what the POH is and then the pH. So that's kind of our plan of attack. Let's write our Kb, put in what we know. Let's simplify. Take the square root of each side. This is my X, or my hydroxide ion concentration. And from there, I'm going to find my POH. My POH is 5.69. So to find the pH, I just subtract that from 14. And I get 8.31 as my pH. We can just double check that it was okay that we took that shortcut where we got rid of that minus X. And so what I do is I take, in this case for the base, the OH concentration, and I divide it by the molarity. So I get 6.7 times 10 to the negative fourth % dissociation. So I am just fine taking that shortcut. This is just a really, really tiny amount. So again, this is just to check. Let's do an example of a salt that acts like a weak acid. So here's the problem. Calculate the pH of a 0.1 molar ammonium chloride solution. The Kb value for the ammonia is 1.8 times 10 to the minus 5. So I need to think, how is this salt going to react into solution? This NH4, it comes from the weak base NH3. And so that means that this right here, this is a stronger conjugate acid. This part is going to behave as an acid. And then I have this chloride ion, and it comes from HCl, which is a strong acid. That is going to be neutral. So what is going to cause the pH in this solution would be that ammonium. So I'm going to write out my equation and show that it loses a hydrogen ion, and then I have my leftover NH3. In this problem, as soon as I find the concentration of that hydrogen ion, then I can take the pH of that concentration. Let's put in what we know into our ice chart. So I have 0.1 is my concentration at the beginning, and none of those. I'm going to subtract a little bit and add a little bit and bring everything down. 0.1 minus x and x and x. And I'm going to assume that this is tiny, so I'm not going to put it into my equation. Let's go ahead and write out the Ka is what we're going to use because this is an acid. And then let's put in what we know. So when I go to retrieve my Ka, I don't have it. I only have a Kb. So I need to do a quick calculation to solve for my Ka. So do the Kw divided by the Kb, and I get 5.56 times 10 to the minus 10 is my Ka. I have x squared on top and a 0.1 on the bottom. So let's simplify a little bit. And then let's take the square root of each side. So my hydrogen concentration, or my x, is 7.45 times 10 to the minus 6. And I take the negative log of that, and I get 5.13 as my pH. So what about cations from a weak base and anions from a weak acid? So what would you do if you have some of both? Well, in this case, you would have to be given the Ka and the Kb values, and then you would determine whichever one is stronger. So whichever one is stronger, then it would have that pH. So if your Ka is bigger than Kb, then your pH is going to be lower than 7. You'll have an acidic solution. If your Kb is larger, then you're going to have a pH greater than 7. It will be basic. And if your Ka equals your Kb, then you'll have a neutral reaction. So for example, if I had this above reaction, ammonium chlorite, my ammonium Ka is times 10 to the minus 10, and my chlorite Kb is times 10 to the minus 13. And so because this Ka is larger, this is going to be acidic. Here is just a table that kind of summarizes what we've been talking about with these salts. Now let's look at acid strength. What makes one acid stronger than another? And there are several rules. And so in your homework and on the AP test, they would ask you to classify acids in a series. And they're going to be a little bit similar to each other. Here's this first series. So this first series, there's no oxygen in the acid. We are looking at the halogens, so fluorine, chlorine, bromine, and iodine put with hydrogen. And the rule is the smaller the electronegativity, therefore the stronger the acid. You could also look at it as the larger the atom, then the stronger the acid. The larger the atom or the lower the electronegativity, that hydrogen will be able to come off easier. So if we compare hydrofluoric acid to hydroiodic acid, I first of all know that hydroiodic acid is a strong acid, and my hydrofluoric acid is going to be a weak acid. But the reason why hydrofluoric is weak is because that fluoride ion is so small, and because of that, it doesn't give up that hydrogen easily. Looking at the hydroiodic acid, that I is so large, then the hydrogen, it is able to leave easier. It, in this series, is the strongest acid. Now, if there's oxygen, the stronger the electronegativity, the stronger the acid. Chloric acid, which would be stronger than bromic acid, which would be stronger than iodic acid. In this one, because of the electronegativity, it is able to hold on to the hydrogen stronger. And it's really the same reason as up above. And then let's look at adding oxygen in a series. So everything's the same. All we're doing is adding one oxygen. The more oxygen that there is, then the stronger the acid. This is why perchloric acid is a strong acid, and all the rest of these are weak. And then the other series that we can do is we can look at removing a hydrogen ion from a charged particle. And it's harder to remove a hydrogen ion from a charged particle, so therefore it will be a weaker acid. So it's easier to remove a hydrogen from neutral phosphoric acid, but once I do, I get this negative ion, and it's going to be more difficult to remove a hydrogen. It can still happen, but it's just going to be harder because this is already a negative. And if I do remove a hydrogen ion, it's going to be even harder to remove a third one. And so as a result, we're going to have and these are all weak acids, but this one's going to be the stronger of this series, and this one is going to be the weaker. Let's just look at this series of adding an extra oxygen to the acid. And I know that the more oxygens I have, then therefore the stronger acid I will have. And it has to do with the oxygens pulling away from the hydrogen ion. So the more oxygens there are, then the more that hydrogen ion is going to be left by itself, so to speak. So by the time I get 4, these are all going to pull together and kind of leave hydrogen off by itself, and so very easily it can come off. This is why perchloric acid is a strong acid. It completely dissociates. When you look at the other ones, they don't have as many oxygens that are pulling away, and so it's less complete.